Hey everyone, and welcome to this explainer. Today, we're embarking on a bit of a mathematical detective journey. We're going to decode the foundational mysteries of squares and cubes. You know, if you've ever looked at a number with that tiny 2 or 3 floating right next to it and wondered what exactly is going on under the hood there, well, you are definitely in the right place. We're going to break this all down using some really simple logic, so it just perfectly clicks into place for you.
All right, here's our game plan for today. First up, perfect squares and roots. Second, we'll explore the world of cubes. Third, navigating fractions and decimals. Fourth, decoding negative numbers. And finally, we'll wrap up with the art of estimation. Let's get right into it.
Section 1. Perfect squares and roots.
So, what exactly is a perfect square? Simply put, it's a whole number multiplied by itself, kind of like making a perfectly equal pair. 2 squared literally just means 2 times 2. 3 squared, that's 3 times 3, which gives us 9. If it helps, you can visualize an actual physical square shape where the length and the width are exactly the same size. That perfect symmetry, that's exactly what we're creating here with our numbers.
But how do we know for absolute sure if a much larger number is a perfect square? Well, we pull out our magnifying glass and use a technique called prime factorization. This is our main detective method. Step 1, you break the big number down into its absolute smallest prime factors. Step 2, try to sort those factors into exactly 2 identical buckets. And step 3, if they match up perfectly, boom. Congratulations, you've got a perfect square.
Let's actually test this method out. Take a look at 36. If we break it down, its prime factors are 2, 2, 3, and 3. We can easily sort those into 2 identical groups of 2 times 3. That's a perfect match. But then, look at 54. Its prime factors are 2, 3, 3, and 3. If you try to make 2 identical groups out of that, well, you just can't. There's an odd man out, and because 54's factors absolutely cannot be sorted into 2 perfectly identical groups, it totally fails the perfect square test.
Now, this brings us to what I like to call the undo button in mathematics. Squaring builds a number up, right? 3 squared equals 9, but the square root, represented by that little checkmark-looking symbol, brings it right back down to its root base. Asking for the square root of 9 is really just asking, hey, what identical pair multiplied together to give me 9? The answer, of course, is 3.
Before we move on, I really want you to lock this into your memory because it's a golden rule. Multiplying a square root by itself magically frees the number from its root symbol. So if you take the square root of 2 and multiply it by the square root of 2, you just get the whole number 2. It essentially acts as a complete cancellation of the root operation. It's just simple, elegant logic.
All right, let's move on to Section 2, the world of cubes.
Welcome to the next dimension. The rule of 3 really takes over here as we transition from flat 2D squares into 3D cubes that have length, width, and depth. So instead of looking for identical pairs, we're now on the hunt for trios. For example, 2 cubed is 2 times 2 times 2, which gives us 8.
To identify a perfect cube, we're going to use the exact same detective method of prime factorization. But this time around, instead of 2 buckets, we're carefully sorting our prime factors into 3 identical buckets. If every single prime factor finds a home and all 3 buckets look exactly the same, you have struck a perfect cube.
Let's test this one out too. Notice how neatly 64 divides up. It's made of 6 2s. We can drop 2 2s into 3 separate buckets, which gives us 3 identical groups of 4. 4 times 4 times 4 is 64. Now compare that to 240. Its prime factors include a mix of 2s, a 3, and a 5. Try putting those into 3 identical groups. It's literally impossible. You're left with mismatched buckets, so 240 is definitely not a perfect cube.
Moving right along to Section 3, navigating fractions and decimals.
Now, fractions and decimals might look like numbers wearing disguises, but I promise there is no need to panic. When we square a fraction, like 3/4, we simply distribute the square. You just multiply top by top and bottom by bottom. 3 squared is 9, 4 squared is 16, leaving us with 9/16. And for decimals, like 0.2 cubed, you just multiply it out. 0.2 times 0.2 times 0.2 gives you 0.008. The core logic here hasn't changed one bit.
And when you need to find the root of a fraction or a decimal, you just calmly apply that undo button to the separate parts. To find the square root of 4 over 25, you just take the root of 4, which is 2, and the root of 25, which is 5. So your answer is 2/5. You're really just revealing the original building blocks, layer by layer.
Next up, Section 4, Decoding Negative Numbers.
Okay, things get just slightly trickier when minus signs enter the equation, but the rule is actually super simple. A negative multiplied by a negative mathematically cancels out the negative sign. That means whenever you square a negative number, your result will always be positive. Take negative 0.5 squared. That's negative 0.5 times negative 0.5. The negatives completely cancel out, leaving us with a nice positive 0.25.
However, watch what happens with cubes. When we cube a negative number, like negative 3/5, we multiply it 3 times. The first two negatives cancel each other out to make a positive, sure, but then that third multiplication brings the negative sign right back into the final answer. This is a really vital clue to remember. Squaring a negative yields a positive, but cubing a negative yields a negative result.
And finally, Section 5, the art of estimation.
Estimation is our high-energy, real-world skill for when you're out in the wild without a calculator. It's really all about creating boundaries. By framing our tricky target number between two easy, familiar, perfect squares or cubes, we can very quickly zero in on a highly accurate estimate. We basically just find a comfortable number below our target, another one above our target, and then we see which neighborhood our final answer belongs in.
Let's see just how fast this bounding logic works. Say we need to estimate 27.5 squared. Well, 27.5 is wedged right between 20 and 30. We know 20 squared is an easy 400, and 30 squared is an easy 900, meaning our answer has to live somewhere between 400 and 900.
Now, look at exactly where 27.5 sits. It's much closer to 30 than it is to 20, right? Because of that, we can confidently estimate our final answer to be roughly 900. And if you actually check it on a calculator, it's 756.25, which absolutely proves our quick mental model got us into the right neighborhood in mere seconds.
We can run the exact same playbook in reverse for roots. Let's estimate the square root of 54. We know the perfect squares nearby are 49, which is 7 squared, and 64, which is 8 squared. 54 sits nicely right between 49 and 64. And since 54 is a bit closer to 49, our estimated root is roughly 7. Take that, calculators.
And guess what? The exact same logical bounding works for 3D cubes too. Let's try estimating the cube root of 180. We mentally check our list of perfect cubes. We have 125, which is 5 cubed, and 216, which is 6 cubed. 180 falls right in between them, but it's slightly closer to 216, getting us to a super reliable estimate of 6 in almost no time at all.
So, you now have all the tools to decode squares and cubes. You know how to sort prime factors into buckets, how to apply the undo button with roots, and how to estimate like a total pro. But as we wrap up this explainer, I'm going to leave you with a little thought to ponder for your next mathematical adventure. If squares are 2D pairs and cubes are 3D trios, what visual dimension do you think happens when a number is raised to the 4th power? Keep exploring that logic, and I will see you next time.